Welcome everyone. So today we are going to start our second lecture for this webinar, which is based on the exploring some aspect of wormhole in modified gravity. And today's speaker is Mr. Sayantan Ghosh, who is a research scholar in Department of Mathematics of BITS Pilani. So this is a second lecture, as I have already mentioned, and this lecture will be, I think, very interesting as we move ahead. So, Sayantan, I think you can start talking.
Yeah, sure. So, okay, if people can join along, I mean, there is no problem because I'll start from little by little itself. So,
No,
okay,
you can start.
yeah,
I think you
sure.
can start slowly. We can move ahead.
Okay, so today actually I will speak mostly about the wormholes because I do not have time to go to the Casimir effect. So I will start with the history of wormhole a little bit because it's meant to be like something which is comprehensible to everything, because black holes are very common word, wormholes are not so much. So as I said previous day, wormholes are like the basic shortcut to hypothetical, and it was Kip Thorne who seriously thought it for Carl Sagan's Nobel. And this is the, I mean, like the embedded version of the wormhole. So now I will come to the history. I'll go one by one. So first, actually, so if you know, like 1915 was the first time when the actually a Schwarzschild solution was proposed, and even in 1916 itself, Flam actually, I will show the picture little later, actually figured it out by some mathematical construction. What we today call is so-called the Koszul extension. He somehow figured it out that if black holes, I mean, somewhat Schwarzschild, I mean, at r equals to 2m, something is going to be funny inside. There could be very well r equals to 2m, like a concept of white hole, which could very well emit. At least there is no mathematical inconsistency with it. So it was a widely ignored idea. I mean, nothing that serious, but you can look at the Flam's paper. So if you see the von Leeuwenhoek Flam's paper, at least it and he writes the Schwarzschild solution in a very trigonometric way. What it is somewhat like how we write today FLRW metric. And this more or less enabled him to actually understand that if there is a concept of black hole, at least in principle, there can be concept of white holes also. Okay, now I come to the at least the father of the wormhole, which most people agree, and that is the Hermann Weyl. And Hermann Weyl didn't invented wormhole to publish paper in relativity, or neither to do some time machine. He was very much a philosopher. So when he was doing so-called the agents theory, that is that if two electrons are interacting, so electromagnetic force, what would this force look like? I mean, from a space-time perspective, and that has to come to his mind that okay, if there is a pure tube, if the forces passing to tube, that should act as a wormhole itself. Like, so in a sense that this was the Hermann Weyl's killing idea, and it is actually one of the article in the so-called Field and Matter in philosophical. And if you see, this is the so-called Stanford Encyclopedia's philosophy one, that it was May's proposal that, I mean, so-called, I mean, the Mach principle, in order to be consistent, one has to incorporate some kind of like the inertia, and the inertia tube could be very well thought as a wormhole. So if somebody I mean, this is something which I do not know, I mean, like the synthetic ontology or something, but at least I wanted to say that the first idea of wormhole was from the philosophy itself. Okay, now this is the first time when Einstein and Rosen bridge. In fact, if you look at the Einstein-Rosen bridge paper, the first citation actually, first they cite the Weyl's idea itself, and then they say that what can be done. So this is the paper, and this is not the paper actually. This is the Matt Fisher's Lorentzian wormhole taken. So let's first look, at least in 5.3, if you realize, it is somewhat like a, how should I say, Risen-Nordstrom solution. But what they found out in 5.4, like if you try to regularize the Schwarzschild solution, say from 5.6, you will get a minus sign out of it. So 5.3 and 5.4, you can see that the epsilon squared by r squared has a minus sign. This is a problematic, because if they really so if they really want to make sure that, I mean, this is a theory of electrons, I mean, this means that the q square equals to -1, which means q equals to I epsilon. That is the electric charge are complex. So this is ridiculous enough, but at least they are happy that at least they could find a theory of charge particle. Like when epsilon equals to 0, it is a pure Schwarzschild solution. So this is so-called the Einstein-Rosen bridge. First of all, note that, I mean, often in like popular culture, even the Thor movies, etc., people confuse wormholes with Einstein-Rosen bridge. Einstein-Rosen bridge are not traversable in a sense that if you compute the geodesics are space-like geodesic. So you have to move faster than the speed of light to traverse the Einstein-Rosen bridge, which is not reasonable. Okay. Now, actually, Wheeler and Misner actually coined the term wormhole, but their paper was not a wormhole. So, if you can see the paper citation, that it is called the classical physics as a geometry. And what they did was, I mean, something. This is a picture from this. They actually took the Well's idea and used the so-called today known as the cohomology theory. So they tried to figure it out that whether the cohomological obstruction can be used in every forces or not. It is somewhat what we today do with Young-Mills theory, like closed form not exact. And this is a typical picture of the Wells paper itself. Okay, so this was the first time wormhole has been coined. That is, the Wheeler actually coined the term black hole also. The point is that a worm is passing through like an apple. So in a sense, that is a shortcut. Okay, now come to our like the research wormhole, which we would do. So Ellis and Bronnikov actually published a paper in so-called the ether drain. Like if ether is draining, how should that do? And the Morris Thorn, that is the second part of it, is the one which we will talk. So the citation B, that is the wormhole in space-time and their use of interstellar travel, is literally one of the best article written ever. So I strongly encourage people who have studied general relativity or basic to read it up. I mean, just to understand how to construct so-called the solution wormhole, which is not given, like Schwarzschild solution or Kerr solution, etc. I mean, if you solve, I mean, it comes from the Einstein's equation, right? I mean, some reasonable T mu nu equals to 0, then you solve and you just solve a PD. But the problem here is that I mean, in order to understand what this metric should be, you have to use a lot of intuition. So this is very different than, I mean, solving Schwarzschild solution. Okay, so this is roughly the metric of Lorentzian wormhole, as you can see, 11.5, which we also did. Now, first thing, note that if I do not want an event horizon, that is the dt's coefficient not equals to 0, you can clearly see that phi has to be like minus infinity or plus infinity. Sorry, phi cannot be like minus infinity or like plus infinity in case like phi is negative. So that is one reason we already taken care of. As long as phi is finite, there is no event horizon, in a sense that a falling particle or a traversing particle would not take infinite amount of time. And B is a choice, which is that in the point is that if it is actually, so if you see, it is exactly like the Schwarzschild point. And B has another motivation, which I will tell the next class when I will talk about the ADM mass formulation, that B actually has a mass dimension of 2m. So if you calculate the so-called the ADM mass of this metric, you will actually get the 2m factor. Okay. Okay, now actually comes the point that where we could cache in some wormhole physics. So one of them is ER equals to EPR paradox, which is very common in string theory right now. Zuan Maldacen, Atul, Leonard Susskind are working. But I didn't want to go there because, again, it's a hypothetical one and it as such doesn't tell us anything new physics which cannot. What it does tells is the November 2022 paper, and this is the traversable wormhole in quantum processor. So I do not know details of it, but I will try to explain what I have understood a little bit. So the point is that you do not construct as such wormhole. You compute something called the SYK model, Subjective model. It is a very good candidate for so-called non-Fermi liquid, and this has a dual model in the charged black hole. Now, instead of wormholes two mouths, it is a SYK model which are acting as a two black holes mouth. And now the SYK model, you are manipulating the so-called the spin interaction by a quantum computer to check that whether the interaction satisfies the duality criteria or not. So in a sense that instead of wormhole, it has become interacting between SYK model, which programmers are very good at creating. So this is okay. So this is sorry, not taken from Lorentzian wormhole. This is taken from Quantum magazine. So in a sense that okay, I mean there are lots of followed by studies which shows that okay, I mean this is not a signature of wormhole, etc. But overall, the idea is extremely fancy. So you not just get wormhole, you get the SYK model construction. Also, you get the duality test also. Okay, now I will come to the criteria of wormhole. So these are not criteria, these are more or less guidelines. So as you can see from the metric itself, as I told, like, okay, the first one is that it has to be roughly spherically symmetric and time independent. And again, you can very well do the stationary, so rotating wormhole or the other kind of time dependent wormhole also. It's just that for engineering purpose, it makes sense to talk about totic. And again, it has to satisfy the Einstein's equation, and the throat should be connecting to asymptotic space-time. So in a sense that for a far away wormhole, we should not have any signature. And in order to not horizon to be exist, phi r has to be finite everywhere. And the tidal gravitational force should be reasonably small. And the travelers must be able to cross the wormhole in a finite and reasonable small proper time. Remember, this is the reason why we need the phi r to be finite to be, because if it is phi r is minus infinity, then there is a horizon, and in so-called the Wheeler tortoise coordinate, the horizon you will take infinite amount of time to cross. Okay, now again, the matter and field should be somewhat related to physics. Okay, so this is the first criteria, that how to manage the throat criteria. So just a second. So remember the Schwarzschild one, if I replace the dr entire thing with just dl, I want to force it into flat metric, I'll get 11.9. Now I can do something. I can actually use the convexity property, because I am embedding in a so-called the cylindrical one. What is the, okay, let me just go back to, yeah. So if you see, I mean, what does this wormhole means? Like, I mean, the shape, like the throat means. So it means that it is convex, provided that it is taken in the z direction, because I want to r, y, z. So you have seen the so-called cylindrical embedding or the embedding diagram even for the Schwarzschild metric also. So what do you do in Schwarzschild metric? You take the dr square as some dl square and check the double derivative whether it is convex or concave. So here also it has been done same thing. So dr by dl has been taken, that is the dr square equals to dr square by 1 minus b by r equals to dl square, and the double derivative has been given. Now what is the criteria for convexity or having a minima? That is d2 or dl2 is greater than 0. And what is the criteria we will get? We will get 11.14 to be greater than 0, or 11.13. So at least we now know that, I mean, not every BR or every phi can be solution. First of all, phi has to be finite. And in order to make sure that their flare out condition is satisfied, the 11.13 has to also satisfy in order to be a reasonable wormhole. Okay, now what happens in wormhole in the modified gravity? So the point is that I'm also talking about modified gravity because these are very good tests for the modified gravity, because the point is that wormhole, as I will show it little later, has to violate something called null energy condition. Now the point is that if you can take care of null energy condition by some means of modified gravity, you would need little less exotic matters to study with. So these are some technical references which I will later send, you can look. And FQ gravity is the one which I work on. Okay, just a second. Okay, so this is the FQ gravity. So I decided I'll not go this much because I'll take the probably next class. And just a second. Yeah, now the energy condition is coming. Okay. So now understand, I will explain what the energy conditions in little later. So first understand that if there is a rho, that is the density, again take the local inertial frame for the purposes. It doesn't matter because the original definitions come from the Lorentz invariant quantity, T mu nu u mu nu. Look at this energy conditions. Now, what these energy conditions are good for? So roughly speaking, the energy conditions are good for to understand that is the gravity sufficiently attracting, because if I give you a mass, if you see Einstein's equation cannot distinguish between plus m and minus m. For example, you can very well write the Schwarzschild solution with m equals to negative also, Einstein's equation would not be able to detect it. Now, how to get that attracting feature, that is something has to put by hand. And that can be done by this energy conditions itself. So in a sense that rho greater than 0, you have to put it by hand. Otherwise, you can very well take minus sign both side and it would not make sense. It would not make a difference. Now I will come to the NEC difference. Now this is the definition of all the energy condition in terms of Tij, Ki, Kj. Null energy condition means that is null like. So in a sense that
Hello.
what is the yes.
Yeah, so I have just two questions, two issues. So when you describe this wormhole, you described something about this cohomology. So Can you just go back to the slide and describe what connection you were talking about this?
No, okay. So I didn't discuss. So the point is that this is the so-called the Wheeler's paper. And if you look at the Wheeler's paper, which I have cited here, yeah, so this classical physics as a geometry. So Wheeler doesn't talk about anything wormhole in a sense that he coined the term wormhole in this paper while explaining that if you want to do the electromagnetic field theory or any kind of field theory, you can think that all the forces are as a cohomological obstruction. Just like except gravity, we can think all the other forces as today the Lie group generated by this. SU2 is the weak force, SU3 is the strong force, U1 is the electromagnetic force. So similarly, it was a Wheeler's pet project where Wheeler and Misner has shown that classical
So
physics
I
can
have a specific question about this. What do you mean here by cohomological obstruction? That if you can explain a bit.
Yeah, so the point is that all the classical force fields, so if you look at one of the your picture from the paper itself, all the force fields are getting punctured through the space-time. In a
Hmm.
sense that now this punctured topology and the non-punctured topology are very different. And this punctured can be explained by the so-called the cohomology of it. Because you
Right.
want the local AMU, so-called the your potentials to be so-called the one forms, and then you can form whether the DMU are closed or exact as a cohomological obstruction. Just like in Young-Mills also we do.
Okay, and that's fine. Okay, so another question is you described about these two SIK models at the boundary, and there is a connecting wormhole in between about that this tensor, some sort of network, this one.
Yeah.
So do you think that these SYK models, this force generally in SYK models, we take these four fermion interaction vertices. So is the case here that SYK models are a single SYK model, or do you think of ensemble of
No, no,
models?
no. It is much more complicated. Okay, so I definitely do not know the details about it. But the
Mhm.
SYK model, which is technically done, is that so-called the four Marijuana fermions are getting by so-called the Gaussian distribution or your random distribution. And yes, you sum up the Mellon diagrams, etc. These are not pure SYK model in a sense that you cannot you put the interaction. So what they did that they use so-called ultra cold atom. I mean, as per I have read from the article at least, they use the ultra cold atom and they use the artificial intelligence to infer that what should be the random interactions. So this is not exactly a lab produced SYK model. Lab produced SYK model, as far I know from my coordinates matter seniors, that it is not possible yet. I mean, I
Okay,
know
but
that
my question is a bit different. So I am asking that if there is a single SYK model, I mean not SYK exactly, but whatever model you are taking, is that a single quantum system, or that is an ensemble of quantum mechanical systems? I mean, ensemble means instead of us, I mean, if you have a wormhole and you have a disk at
it's
the
an
boundary,
ensemble of
right?
a system. I mean, it's an ensemble of a system where the specific interactions, I mean, the interactions are in general, how should I say, Gaussian distribution,
Hmm.
and the interaction has been manipulated by some sort of yeah, qubit interaction.
Okay, so you are so
Well,
the model
I would think
specifically.
so. I mean, I mean, I do not know. Maybe the Nature original paper yeah, has the yeah, details of it. But the point is that they actually induce the interaction or the Gaussian distribution by artificial intelligence itself. So that much I know that. I mean, one Caltech graduate did. So in a sense that it is far from the so-called the SYK model one somebody yeah, does in the non-Fermi liquid course or something like that.
I see. So it's not a single like model, it's a ensemble of systems, and both side of the boundary you have that sort of system, and there is
Yes,
a connecting
and
qubit. Qubit is exchanged or something like that.
yeah, if the qubit is exchanging by some noise to ratio, you can say that information is actually traversing through a wormhole. So yeah, it is farthest from the anything practical or even useful, even or conclusive. So that's why if you see there are thousands of follow-up papers which are more or less claiming that it
And
doesn't do
you
anything.
mean wormhole means so you are using two terms. So one is traversable wormhole, another is wormhole. So
Yes,
Einstein-Rosen bridge has a space-like path, so that is not traversable at all.
yes,
But if you have wormhole, when you are saying wormhole, that is traversable in the sense you are using,
yeah,
or when
yeah,
you are
yeah, yeah.
using traverse.
So if you see from yeah, this slides onwards, I will only talk about the Morris-Thorne wormhole.
Okay, okay,
Mm,
okay, okay, fine.
yeah. So if you see from the 12 itself, so everything now is traversable wormhole. In fact, the special part of a traversable wormhole, so-called the Morris-Thorne wormhole. There are Ellis-Barnikov and other type of wormhole, traversable wormholes also. This is what we will talk about. So our metric is this only.
Okay.
Okay. Sure. Now you can see that what we have done is that we have actually given a proof that redshift function has to be finite. And the second part, as you remember, the flaring out condition we have done. How did we do it? We did a cylindrical embedding, and from the cylindrical embedding, we from the cylindrical embedding, we use the convexity criteria to derive that, and that is the asymptotic flatness criteria is just like the Schwarzschild one, because the ratio itself has to go to 0. Okay, so this is the Q term, which I will probably do later. Let me just go to the null vector where I was. Now, what should be a null vector in say t r theta phi direction? It is reasonable to take 1 minus 1 in a radially outgoing, and if you take 1 minus 1 or minus 1 1, whatever your signature is, you will get rho plus p greater than equals to 0. So in a sense that any particles which are actually filling some sort of T mu nu should be greater than equals to 0. Now, why it is greater than equals to 0? It is comes from the attracting principle. Okay, so this is the null energy condition. Null energy condition. Now I will show you that why wormholes violate the null energy conditions. Okay, so this is the so-called the famous Roy-Choudhury equation. Actually, there is a very good discussion in the Kipthon's book. I mean, I didn't cite it because it is not a scientific book. Black hole time warps, and he actually tells details about he actually figured it out that why it has to violate the null energy condition by bare brute force rich tensor calculation. And Don Page actually told him the global trick of Hawking and Ellis. So if somebody is interested in a little bit popular literature, can look. Now I'll tell a little bit about what the Roy-Choudhury equation does. Theta is so-called the geodesic deviation. So everybody here is familiar with Roy-Choudhury equation or not? Like, okay, so okay, so maybe I'll just explain a little bit what does the Roy-Choudhury equation says. So roughly, if you start from the north pole, all the geodesic, and you want to see that how the geodesics are deviating from each other. This is given by Roy-Choudhury equation. In a sense, that geodesics would deviate based on the curvature, which is reasonable because for a sphere, geodesic deviates more. For a plane, geodesic deviates less in a linear, and for hyperbolic plane, geodesic deviates very less. So it should depend on the curvature. Second, it should depend on so-called the shear of the geodesic, in a sense that a storm of particles are going, what shear are they are going, and then they should depend on the theta itself, that is the geodesic deviation, and they should depend on the rotational also. The reason why Roy-Choudhury equation is called Roy-Choudhury equation, not the Landau equation, even though Landau wrote it down in his classical field theory much earlier, is because the include of rotation term, and include of rotation term was not there in the Landau's book, and Roy-Choudhury himself later told one of the interview that he was motivated to include the omega term based on the Gödel's paper. That Gödel actually showed that, I mean, under certain reasonable condition, rotating metric can happen without violating any without having any singularity. Now, as that's we got, we are quite fortunate. So we now take the geodesics which are radially falling. That is, there is no shear, sigma is equals to 0. There is no rotation, omega equals to 0, and we only get the 12.54. Now we get that if that geodesics are satisfying in a throat. Remember, at the throat, the geodesic deviations are 0. That is the theta deviation, just like the how should I say, great circle of a sphere. At the great circle of the sphere, the rate of change actually is 0. In fact, you can calculate that what should be the rate of change throughout the sphere. It is the cos theta. Okay, now you can see that when the theta equals to 0, 12.54 becomes r mu nu this. And now, because the, just a second. Okay, maybe one picture would be more. Now, if you see this light rays through the wormholes has to diverge, and this was the problem, that light rays under any mass always converge. It always acts as a converging lens. So if the light rays has to diverge through the throat because we want to pass through the one, and then the only option would be to take r mu d theta d lambda greater than 0. That is r mu nu k mu nu to be less than equals to 0. Now, this is same as the T mu nu, K mu nu. You might ask that what happened to the other trace of it, because you know it, this is the null geodesic, so trace of T is equals to 0. Okay, so now we get the R mu nu, the total integration is this. And so as you can see, that 12.56 actually shows that in order to have the throat stable, one has to violate the null energy condition. So this is just something we have to live with it. And this is a global argument because Roy-Choudhury equation is true under any circumstances. So even if you put some shears, etc., you can use the same kind of Hawking or Penrose's singularity type of arguments to conclude that indeed null energy conditions violation has to happen. Okay, now I will talk a little bit about the Casimir energy. And okay, so this is the Casimir force, and the reason why it is interesting is that this is the bare brute force explanation that why quantum field theory is correct. So in quantum field theory, we take an infinite amount of oscillators, and we ground state of the oscillator is always half h cut omega. Now you can ask that what happens to all the ground state. Now the details experiment is very, very difficult. In fact, the first Casimir effect experiment was done not using the metal plates or anything, using the helium bubble itself. So you can look at our paper, we have cited a little bit details. And this Casimir effect is actually given by this expression. Now, you do not have to understand how the exact thing is done. In fact, without proper understanding of quantum field theory, it would be too much hand-waving argument. So roughly speaking, that all the mode sum, that is the 1 plus 2 plus 3 plus this, would actually turn out to be so-called the -1/12 by under some regularization. So that is one way of doing it, as Padmanabhan does it. And the standard derivation, which is done in the Z's book or in other Kardars also, you can see like the 3-dimension version. They do it using the so-called the momentum cutoff. Like you take the arbitrary momentum and cut off at the certain length, and you make sure that your force is such that the length cutoff does. And this is a very good exercise because this is the first time which shows that how the regularization should be done, not the renormalization, but the regularization. Okay. So the verification is done actually in Lamarck's PRL paper, and yeah, it was an amazing paper because the point is that they used to have liquid helium to use this. Okay. Okay, now we are almost there in our F2 gravity, so maybe I will not talk about, but just take that just like the Einstein's equation, you need the field equation to satisfy something called G00, G11, G22, G33. In our calculation also, FQQ, there is PR, PT, and rho equation. So this is the rho equation 19, and this is the PR, and this is the PT. And this is the big FQ equation, which I will not go into. So I'll just go through that, how certain researches are done. Okay. Now I'll tell that this is the rho we have taken, and this is the BR which we have solved using the Mathematica. Okay. So, and this is the PR and PT we have gotten. Now remember that what should be the BR's criteria should be? BR should be tending to 0. I mean, BR by R should be tending to 0. So that means BR tending to 0 is a sufficient condition, which we can see. And B prime R is also tending to 0, which, less than 1, which is expected. That means why B prime R is less than 1? Because we talked about the throat condition, because the cylindrical embedding should be convex. Okay. Now, what about the NEC condition? Now, remember we talked about that for the reason actually the NEC condition in modified gravity always does not needs to be like violated, and the reason comes from the Roy-Choudhury equation itself. So, if you look at the Roy-Choudhury equation, this for modified gravity, R mu nu is not just so-called T mu nu minus T. It should be with other modified terms also for the non-minimal coupling. And that could affect, but in our case at least, we got the null NEC for the radial pressure. Now, why does the one takes radial pressure? This is a technical one. It was actually Matt Fisher and Norris Dodici who figured it out, that actually wormhole would only affect the radial infalling part. So if the lights are radially infalling NEC, the only rho plus PR has to be violated. Rho plus PT doesn't need to be violated in a sense. Okay, now I will come to the one that what one does with the Casimir one. So we talked about the parallel plates Casimir. Now you ask that, okay, now that is not engineering feasible. Like, I mean, if there is a plates, two plates, like how you take the extract the energy to charge the wormhole throat. So we proposed a secondary mechanism, that is that if you take to sustain the two cylinders, what should be the Casimir effect of this? Now, how do you even start calculating the Casimir effect without the normal plates? So, any ideas? Okay, so everybody remember that for a like cylindrically charged one, what we do in the electromagnetism, like the Jerry Jackson, like what special function one has to study if one has to study with the cylinder? It's spherically Bessel function, probably. So you have probably learned that if there is a cylindrically charged one and one uses the spherical Bessel function as a solution of the charge problem. Similarly, also you take the two boundary condition and you use the spherical Bessel function to find the modes, and you sum over the modes in form of spherical Bessel function to find the Casimir force between the two cylinders. And this is the form which is given where L is the length and gamma is so-called the B by A is the outer radius, B is the inner radius, and this is the 27 is the big expression, and this is exact in a sense that you can mode over all the n's from 0 to infinity, and in and kn are Bessel function of first kind and second kind. So this is actually calculated in these two papers which is given in the citation. Now you can first think that, okay, I mean, this expression is almost like impossible, and there is literally a 0 to infinity integration is lurking, and while there is a n1 also multiplying. Now, how to bypass that? Fortunately, that is also can be done. Bessel functions are very well known. So in a sense that under your certain like the tolerance to approximation, you can always check the Bessel function on, and you can get the following energy formula as we have talked. And this is the energy we will use. And the density is so-called the sphere, like the density of the cylinder would be pi of b square minus a square. Okay. Now we have solved the BR, which is significantly bigger, where F1 is analytic. But at least good thing is that it is analytically solvable. And now let's see whether our litmus tests are correct or not. BRs are almost going to 0, or at least BR by R would definitely go to 0. And B prime R is still less than 1. B prime R is more important because the point is that we want a throat rather than the asymptotic freedom also. Sorry, asymptotic Minkowski also. Okay, and this is the rho, and this is the PRPT. So just to clarify that how one does it. So we put the rho expression from this in the Einstein's first 0-0 equation. We solve for the BR, then we put the BR in the 1-1 and 2-2 equation to get the PR and PT. Okay, now the NEC condition again. Hello, remember for the
Hello, Sayantan. Just let me inform you that we have only 30 minutes. Okay.
Yeah. So I'll be done within 10 minutes. Yeah.
Okay, fine.
Yeah. So okay. So okay. So the point is that again, P plus PR is actually negative, which is somewhat of a good news. Actually, this is actually, I would say that little subtle that because we in the FQ gravity, we choose a linear model, and in linear model more or less tends to mimic the GR. So that's one of the reasons why we are getting so much consistency, but at least it is exactly solvable. For example, in nonlinear we tried and it is literally not solvable. You have to choose some B or something. Okay, now Casimir effect on two spheres. So this will be the last theme of the today's talk, that now I am not taking the two spheres. Okay, sorry, just sorry. So I'm not taking two concentric sphere, if you can see, and two sphere which are separated by this. And there is absolutely no way, like if I give you two charged sphere also like this and find the potential or something like that. Sorry, what is the self interaction of this? There is no way you could probably do it, because I mean the one point of the sphere is not seeing the other part of the sphere's full thing, etc., etc. So how do one even start doing Casimir effect with two sphere? Now image should be clear that we want to put our wormhole with two spheres at the two throat to check in between what is the Casimir effect. Is it clear, the picture, that in the mouth of the wormhole we are putting the two spheres? Now, how do one even calculate this? So, I mean, of course, I could not do it. I actually started doing some literature in the condensed matter physics. And in the condensed matter physics, I actually found out that, I mean, it was a PRD paper, but it was motivated by some of the other condensed matter. They used something called the diagrammatic method. So, in a sense that up to numerically, you know that what should be the interaction between both of them. And you solve the interacting terms only taking the so-called the T operator, that is the one, and you only take the so-called RPA diagram, and you get an expression like this. Now, remember, there are lots of approximation involved. The first one is, of course, the distance is much larger than the A. So remember, the A is the radius and D is the distance. Okay, and this is the energy equation, which is little ugly, but at least we got an energy equation to that. So if you see that it is a condensed matter journal which has actually given this, and they are using it to find the van der Waals force between the two molecules. Okay, now we can do a little jugglery as we are doing. We again calculate the rho, that is the pi a squared d, and we calculate the pressure by the thermodynamic relation, and this is the pressure. Now, actually, we bothered about only one case, because the first case is that d is variable, and because we want to squeeze change the location of the two mouths such that whether wormhole is stable or not from the engineering perspective. But when we submitted to EPJC, actually the reviewer actually asked for the second case also for the completion. So the first case is that d is variable, that is the distance between these two are changing, while the throat itself is constant, that the radius is constant. And this is the shape function we have calculated. And yeah, so again, now there is a little problem that B prime is little bit increasing, but at least it is less than 1. Now, are we bothered that it is increasing and it would eventually shoot out to 1? No, it just means that your radius, so-called the throat radius, should not be further than this. That means you cannot have a wormhole up to, say, like here to New York, but you can at least have a laboratorical wormhole in the R in natural units to have that. So this actually gives a constraint of, if you want to use like the two cylinders as a, two sphere as a wormhole, what should be the constraint of this? Okay. And this is the NEC we have calculated. H1, H2, H4 are all the elementary functions. So in a sense that this model is exactly solved. So you can look at our paper for the details, which I will cite it later. Okay, now NEC is again getting solved, which is actually good. That not solved in a sense that NEC is getting violated, which is again a good notion that, I mean, also not very surprising, because we are using the Casimir effect nevertheless. And for a particular radius and particular R0, we have plotted it for various values of the model parameter. Alpha is the model parameter, so we have taken alpha q plus beta in the FQ gravity. Okay, now this is the second case is coming. So when A is variable, D is constant. I actually do not know like what is the motivation for that. Like, I mean, why would you change the sphere radius while keeping the distance? But reviewer asked it for the completion, so it's probably good. But at least we would be surprised if it didn't work out. And as you can see, that B prime again having a similar value, while the NEC is again, the NEC at this point is actually getting satisfied. Now, I do not know what is the direct reason to that. I think that when you are changing the radius while keeping the distance, due to you need less Casimir effect to keep out the throat. So I guess that is, I mean, somehow cancelling the effect. So this is something which I also as of now do not know, like why is the reason that here it is Casimir null energy condition is getting satisfied in the that is the sphere case 2, and that is that A is variable and D is constant. Okay, so this is the okay, so I'll probably not go into details, and this is the work which we have published, and fortunately, it was in the right time and it got more than, like, I guess at this point, 55 citations. So if you want for the details, at least you can probably look into this. It is in the archive also. So yeah, I mean, I just wanted to say that, I mean, it's somewhat good that, I mean, like, even the wormhole topic like wormhole, which still has some relevancy in the context. And yeah, and after especially the SYK model and the Google computer are using more and more qubit to accurately calculating wormhole. So it is a fertile place to start doing research. So in the next talk, I will talk about our second paper maybe in the GAP, which is as a Parthoda also suggested, like the little bit of non-commutative. I will tell at least from our point of view what we have done. So any questions? Okay, so this is where I stop. I really have to catch a train. So yeah.
Yeah. It is a really nice talk, and it is a really nice explanation for this kind of discussion on wormhole in modified gravity. And it is a time to take the questions. Are there any questions from the audience? Please unmute yourself and you can ask the questions. So please unmute yourself if you have any questions from the audience. Or you can send it to the chat box. Okay, if you have no more questions, then it indicate that this is going well. But I want to ask some questions regarding this talk. Could you tell me that what is the predictability on this modified gravity using this kind of setup?
Yeah, so
So,
that would. So that we will discuss in the our third lecture, where that is the first time we have given a little bit of phenomenological flavor. That so that's the spoiler alert. Like, what we have done is that we have actually said that if there is a thin shell around wormhole, and what should be the potential of the thin shell, and the potential, the shape of the potential, that is the ISCO or the stable circular orbit, that could at least in principle tell that what should be the wormholes like. Okay, so of course, I mean, the reality and the phenomenology or theory is completely different. So there could be many things, but at least I would tell that if you say want to see an object and you want to somehow distinguish what makes a wormhole from a black hole or other astrophysical objects, there are many ways, like the check the light paths, etc. But we will focus on one aspect that is we have personally worked on, and that is what is the effect of the thin shell. And the thin shell, due to some Israel junction condition, would have some potential, and those potential would deflect the light very differently. So if somebody find those lensing corresponding to thin shells, that could be at least one smoking gun to that. So that would be the part of the next lecture, the last lecture.
okay.
Or you can just look at my thin shell paper also, like, I mean, as I have cited the previous day.
Okay, okay. So do you believe that on the my other question is that do you believe that this modified gravity is necessary, or is it incorporated effect of the dark matters?
No, okay. So it's very unlikely because of the so-called the CMB result. Okay, so this is quite deviating, but point is that, okay, you can always modify your gravity such a way that you can take the halo structure.
My question is more direct question is that which guideline predict, or what is the basic guideline to indicate that we need a modification in the Einstein theory of gravity? I mean, what is the basic
there is
guideline?
I mean, there is no basic guideline, I would say. I mean, it's like asking that what is the basic guideline that we could say that we understand the quantum mechanics or the wave function collapse. I mean, we don't. I mean, we just calculate it, and hopefully that. So, for example, you can always push a further, like, so for example, let time acceleration. Is it caught by lambda? Or the modified gravity would say that why doesn't your lambda matches with the theoretical cutoff calculation? That is the 10 to the power 120. Also,
In the context of quantum mechanics, what you are suggesting, the context of quantum mechanics, the collapsing nature of the wave function, there are many proposed theory which provide the guidelines why this situation is appear. So this is the observation. So my question is that what kind of observations suggest us that we need some modification in Einstein theory of gravity? Do you follow my questions?
Yeah, but I'm actually saying that that is like the, for example, wave function collapse is a fact. Now, what could be
Is
the
a fact.
underlying? Yeah,
Yes,
what could
I
be the
understand.
under?
But here, what would be the fact which tell us that we need some theory of modified gravity, or what is the, what is the, which encourages us to modification in the gravity?
So that I cannot say certain, because the point is that as of now, I do not know any single article which written in the modified gravity does not reciprocate in the called the lambda CDM with twitching a lambda little bit, twitching a CDM also, even in the wormhole also twitching the quasi-normal modes, etc. But I can say the other way around, which is the Starobinsky or original idea for the FR inflation. Starobinsky at least realized that, I mean, if you take the scalar fields as a inflation, I mean, roughly speaking, so you always have to put a cutoff on the FR gravity, like the R beyond R coupling. That also comes. I mean, the full quantum gravity is not known, but if you take the spin massless spin to interaction in linear model, you will get the, at least in the linear of FR, you will get the Pauli action, Pauli phase action, and beyond the non-linear, of course, there would be some corrections to R also. Now, you might say that, okay, I mean, that is I mean, what about the covariance, etc. So that's why Starobinsky's original idea, I mean, I actually heard a little bit from Mohammed, I mean, I do not know the details, but at least Starobinsky's argument was that if you put a cutoff in scalar field theory, saying that, okay, it is reasonable for the renormalization, and at the end of the day, I'll get rid of the cutoff. It is as reasonable as putting the alpha FR also, or any other modified one also, saying that I am cutting out the graviton-graviton interaction before the non-renormalizability happens, or something like that. So this is, I would say, that the best argument in my personal test, I have found that if you take the scalar fields to be, I mean, whatever your quantum field theory, with a coupling constant not discomforting, you should not be discomfort with the FR also, because it is the one loop correction of the two graviton-graviton interaction also.
I see. Okay. Okay. So it's good. So let us thank the speaker again. And if you have no more questions from the audience, then we can stop our discussion, and we'll again come back for the third lecture of this webinar.
Sure.
This mini school.
Yeah,
Okay.
actually, this was a little bit challenging for today, but yeah, I hope it went well. And also, yeah, I'll send you the slides, and you can put it. Okay.
Yeah.
Sure.
Sure. Send me your slides. It will be better.
Okay.
Okay.
Sure.
Thank you. Bye bye.
Thank you. Bye.